leave a comment, and we're all here to work together. So last week, we learned about what is MLOps. So we saw how it was different from AI ops, data ops, and all of that. And then we got into the nitty gritty. So we understood the bias and the model selection. So I'm going to create a playlist in case anybody missed it. Please go and check it out. Today, we are going to start understanding the different components of the MLOps production system. And think about it, we are specifically working towards having an application in mind and ensuring a machine learning model gets into a production phase. So that is what we are trying to do. We are, of course, we will focus into scalability, but scaling an existing application is not what we are trying to do right now. That is a very different focus, different mindset. And again, the tool chains are also going to be different for that. So think about these applications, the examples that I'm showing you every week is, let's say you are in a startup, or even, let's say you have an existing product, which is not using machine learning, but now you have ML in the back end. You want to make sure that it gets to this phase that multiple people can now access it. And again, this would be something which is not on-prem, which is not on premises, but this is using the cloud, cloud solution. So you could have, GCP, AWS, Azure, any one of them. So today we are going to be talking about data pipelines. And when I say data pipelines, it is maximum of the ML engineers, their time goes into getting and sorting data. Because data is typically, whenever you get data for any real applications, it is not clean. You have to ensure that it is clean and put in a particular format. If you're talking about images, then you have to make sure that they're all contrast adjusted. You have to make sure that if you're using deep learning algorithms, their sizes are same. If their sizes are not, you'll have to maybe crop them and ensure the crop sizes are the same. So there's a lot of business case dictated paradigm that goes into cleaning the data. But whenever you are even in the process of getting annotated data, or whenever you are in the process of saying, okay, now let me get started in obtaining good quality data, typically the data pipelines happens independent of the modeling pipeline. So modeling and data collection and annotation typically is asynchronous, because if you are waiting for one to do the next, you will never get things in time. So that's the reason why this data collection, data cleaning, and all the pre-processing part is typically an asynchronous process. So let's start with the ML production system components, and then we will get into the exact component that we are talking about today. Again, this is going to be the diagram that I show on every single session. So again, the data pipeline is the first part of this whole process, where you have initially thought about what the configuration is going to be. What's your business case? What are the metrics that the business case is asking you to get on with? And then you have to do some amount of data collection. There has to be some amount of data verification and feature engineering. Let's give you some examples so that we are following it as we are putting things together. So if you're in autonomous drive, let's say, and you want to do object detection, but now you want to do a little more challenging job, which is object detection at night. So the first job would be to collect data. So you would have maybe an autonomous drive car, and it goes around the city, and it is collecting. Of course, it is all you're logging are videos. And then once you have these hours and hours worth of video, you need to make sure these are good quality, right? So there's a quality verification that happens. And then you're not going to pass all of this, let's say 8-9 hours of video into a machine learning algorithm. First off, you need labels for each and every one of them. And second, again, annotating everything is going to be, you're not going to have any money left after that. So the first thing you have to figure out is what are the images that you should be extracting, that you should then send for annotation, that is going to make sense. And once the annotations are come back, you have to also do some amount of quality verification to see, are these good quality annotations? Can my data model work with this? Because if you start with poor quality data and you don't know if the quality is poor on all of them or not, your model is essentially going to fail. So you don't want that to happen. So that's the reason why understanding the data pipeline is extremely important. Now, nowadays, there are a lot of companies that are investing in making this data pipeline for you. So, there are a lot of labeling companies, and they do ensure quality, processing. while you get your annotated data back. But if you are still this company who has outsourced the data collection or the data annotation, you should still do some due diligence in order to ensure that the annotated data that you've gotten back is of the accurate quality that you're interested in or not. And today we will see how to do that. The next step after that would be model pipeline. So this model pipeline would be essentially in this case, once you have the data, it's put in one place, it has some metadata associated to it. Then you're trying to figure out which model is the best in this particular case. So again, hyperparameter situation, selection, and that particular situation that most of machine learning engineers are pretty well adept with. But in this case, there's also this thing of online versus offline monitoring. So think about it. Of course, when you have ground truth or when you have the actual labels, you can very easily figure out that, yes, this is accuracy, precision, recall, F1 score, and so on. But if you are putting your model in runtime, there is no way you will know the actual label. In that case, that's called your live monitoring or online monitoring. In that case, the parameters that you are detecting is actually not going to be accuracy, precision, recall, and F1 score. It's going to be something different. And in these cases, these are typically probabilistic because your models are probabilistic. You can look at the maximum probability, you can look at the minimum probability, you can even look at the per batch mean probability. So stuff like that you'll have to now look at rather than very cut and dry accuracy, precision, recall. And finally, again, there is the deployment pipeline, and again, we will look at it at length. So now today, let's focus on the data pipeline per se, right? So like I mentioned, the first step always should be in which you make the project setup decisions. So for today's project, the sample data set that I'm taking, again, it's a medical image data set. I know most of my subscribers, they are working on medical images. So I decided to go the medical image route. And again, I'm using fundus images in this case. So for your retina. The goal in this case is, again, you would look at a fundus image and you would be able to say if there is pathology or not. So ideally, this is a classification task. But you can also look at it from a bounding box. So if you have an image, you can also put a bounding box around the regions of interest, or you could do semantic segmentation. So most of the research, existing research, it has actually shown that in order to do best classification, the best method is actually semantic segmentation, because in that case, even if you are detecting a few regions of interest, you have a high confidence that this image has lesions or not, or this image has pathology or not. So the best way to classify is actually doing semantic segmentation. But as we all know, semantic segmentation is costly because you need an image to come up from, right? So that's the reason why in a lot of cases, you just choose the normal classification route. Then I talked about the offline metrics. So accuracy, precision, recall, anything that requires real labels, that's called offline metrics, because this is not something you can live monitor. You can take a batch of it. You have to again look at the ground truth, and then you can come up with the offline results. That's the reason why you cannot live be predicting accuracy, and that's why the categorization as an offline metric. Then you have online metrics. Online metrics typically, in this case, in the context of image classification, it could be things like image quality. It could be signal to noise ratio. It could be blurriness, and I will show you each and every one of them in the data pipeline code that I have prepared. And finally, you have to also take into consideration what is the format of the annotation. Is it typically just a JSON file? So if you're doing classification, you'll just have image ID and the labels, right? Is it an XML file? Again, very similar. Or if it's images. Now, I do get this question a lot. If I'm doing semantic segmentation, if I have an XML file, can I convert it into an image? The answer is yes. So Label Me has a plugin to do that, and there are several others. So if you just type XML to image conversion Python, there is a Stack Overflow page that tells you, step by step how to go about it. All right, so let's look at the data pipeline today. So let's say that I have a lot of these fundus images, sample input images, and I'm putting this into the annotation pipeline in batches. So always remember, in order to do image annotation, or it could even be for language cases, it's always best practice to use at least 2 annotations per image. And the reason for that is, if you just use one, you would not know if this one annotator is good or not, right? You literally have to manually look into every single image in order to figure out if the quality was good or not. However, if you start getting 2 annotations per image, this is where you can very cleverly now start putting in automation, because you can start seeing how much 2 different people agree or disagree. And if you see a particular image or particular batch of images where 2 people are absolutely disagreeing, you will know that this is probably a one area or one batch of images that the inspection, an expert needs to go in and look into. Right? So, and you will only be able to get this if you have at least 2 people looking at the data quality. So, and typically these are actually more than 2 as well. And again, different companies have, different labeling companies have their different approaches. Some of them typically would say is if there is a batch where there is a lot of disagreement, they would randomly sample some images from there, and then there would be an expert who would look at them and say which one. So let's say annotator 1 and annotator 2, which one of them has done a better job. If annotator 2 has significantly done a better job than annotator 1, all annotations from annotator 1 would be dropped, and only annotator 2, their work will be taken forward. Again, this is just one way. Again, there are multiple ways of doing this as well. You can also run a deep learning predictor and see how much it agrees or disagrees. But again, a deep learning predictor, it's a little because again, if the model has not seen images of this kind, it's not going to do any a good job. So that's the reason why having 2 manual annotators annotate, and then understanding which batches are questionable, using the disagreement between them, is a better idea. Next, you get into evaluate annotation variabilities. You select the best annotator. Like I mentioned, it could be manually randomly selected, or you can even have a deep learning algorithm or a machine learning model to tell you how disagreeing it is from that one annotator. And then finally, you store the metadata with compression. So what that means is there will be some metadata that the business case is going to dictate. So for the fundus image in this case, there could be metadata such as ethnicity. It could be hair color. It could be eye color. It could be age. It could definitely be, because there are a lot of models that are actually looking at fundus images and trying to predict age. So, and then there could definitely be pathology, if there is exudates or not, if there is red lesions or not. So all of them, now they become metadata. So just storing an image as is, like I mentioned, data pipeline is an asynchronous process. So whenever you're storing an image, you definitely would like to compress it. You can use autoencoders to do that. But also, you should also put a metadata to it, so that when you're searching in the future, maybe you only want a particular batch of data that has that corresponds to a particular ethnicity and hair color, or you want a batch of data that corresponds to only pathology, only that have red lesions. Then you are very quickly able to search. So your information storage and retrieval becomes very simple in this case. And you're essentially just going on looping through this whole process till you get quality annotated data which is stored. So again, I gave you an example of medical images. This can scale very easily for any other applications that you're talking about. The metrics are going to very much change if you're using autonomous drive or indoor images or satellite images. In all these cases, your metrics are going to change, and your expected the metadata tags that's going to come up, it's very much going to be dictated by the business case. All right. Now that we have covered the basic part, let's get into the collab that I have prepared for you guys. So I first wanted to walk through the data set that we are talking about. Again, this is a very simple diabetic retinopathy data set. It's the DIRETDB1. I'm going to be mentioning the link in the description box below. So here you have 89 images. These are the 89 images of the retinal images. I've put everything in Google Drive just to show you. Again, if you have your local version of Python, that's completely fine. And then this particular data set has 4 different kinds of annotations. So there's soft exudates, hard exudates, red small dots, and hemorrhages. I just wanted to show you what each and every one looks like. These images, again, your annotations should always look like black and white images. But if you see in this case, you have grayscale as well. The grayscale actually tells you about confidence. So if you look at the pixel value, some of them are 0.5, some of them are 1, some of them are 0.9. It just means that how confident you are that a hard exudate or lesion exists in that region. So ideally, in order to generate a black and white image from this, you are supposed to threshold it, very easy thresholding. If you just threshold above 0.5, you're going to get all of the regions that are most probably, pathology versus not. So again, this is just one way in which I'm using an image. Yeah, my input is my image, my output is annotations are also image. How would I go about finding the quality in this case, right? So that's the problem that I'm trying to solve. So this is the code that I've put together. I'm going to be, running through it so that we are all on the same page. So first step, what I'm going to be doing is location. So let me quickly go over what I was talking about. So first off, you connect it to the drive. And again, in the drive, as I had mentioned, you will see that, these are the different folders that exist. And here, I'm going to be using the DB1 fundus images, and then there is this DB1 ground truth. So fundus images is going to help me figure out what is the quality of the images, and DB1 ground truth is going to tell me what is the quality of the ground truth that I have. So first off, I just printed what is the number of images in my folder. And then I'm going to be extracting different properties for the images and different properties for the ground truth, right? So for the properties for the images, what I'm extracting is, first of all, I'm looking at the blurriness, and then I'm looking at the PSNR, or peak signal to noise ratio. Both these values, higher are better. So this is the code where I am actually running it. So as soon as I ran this cell, I was able to see that, okay, these are my image numbers. And now you see that in this case, there is this one image where the values of the blurriness index and your PSNR index is little different from the other images. And again, this code will be available to you guys so that you can try it out. You will see the blurriness is, again, that's a variance of Laplacian. I'm using the Laplacian filter in order to reduce the variance in the images. And then whatever it's returning back, I'm computing an index based off of that. So again, ideally, if you have a blurry image, you will get a very small index, right? And the other thing is I'm using the PSNR, or peak signal to noise ratio. How PSNR is computed is when you have, when you take an image and you sandpaper it, you get the, background goes away. You're just extracting the edges, essentially. And then for the edge image, you are trying to, figure out how is the, input image different from this compressed image that you now have. And I have functions for both of them up top. So as soon as I have, I print both of them together, now you're able to see that for one image specifically, these two are distinctly different. And again, SSIM I didn't use in this case because these are medical images. Now, if I use SSIM for all retinal images, it's going to say everybody is SSIM1 because they look so similar to one another, right? So SSIM is not a useful metric if you don't have video data. And then I got into annotated images. So now I'm coming up with the metrics for annotations. So this is just to show, what an annotation would look like. So in this case, I'm just thresholding it above a pixel value of 0.9. Again, everything has been scaled in 0 to 1. If I had done 0.5, I would have seen a different region of interest. You see now this circle is bigger. So this is just thresholding because I showed you the images were thresholded, right? So here, as you had seen, in this particular case, the images are thresholded. So now what I will find are two different metrics. One is the mean pixel value, and the second one is the coefficient of variance. The coefficient of variance is, again, standard deviation over mean. So as soon as I run this, again, I see there is this one image. For this one image, I see the coefficient of variance and the mean pixel value is distinctly different. So this is actually files 3. So let me look at the name files 012. And this is image 005. So let's look at image 005 and why it is so distinctly dissimilar. So now you're now able to figure out that image 005 has something in it which is very different from the other images in its batch. So we can actually do some research and then see where your image 005 is. And mostly you will see the brightness and the contrast and stuff like that is very different for that. Here you have image 005. Of course, as you see here, the image 005 has a lot of lesions. You see, this is much more brighter than the others. There's a lot more lesions than all of the other images. So clearly this is very different from the others. And that's the reason why the data model is telling you. Do you have to do something in this case? Ideally, you should do some amount of contrast illumination exercises in order to reduce that. So that would be what we are doing in this case. So this code again, I will be made available to you so that you can all try it out and see for your data sets, if you're using images at all, how your metrics are being different, and how you can use this for your quality checking for your own data sets. I see a couple of questions. Can you say about the data sets that will be useful for image storage? That's a good question. So the databases, again, it's very dependent on your use case. For some situations, some companies don't want to use cloud storage, right? But again, there are some companies that I know that they like to put their data in S3 buckets. So Amazon S3 buckets is very common. There have become also a lot of annotation devices that can handle S3 buckets. So they just take in S3 buckets as input, and they are very clearly able to give you the annotated format. Same goes for GCP data buckets as well. So you can even put your data in GCP buckets. Compression formats, very dependent on, again, the kind of industry that you're working for. Medical images, typically compression is not suggested because very small change can say that your image quality has been destroyed. So if you're looking at a very niche MRI image or a very niche CT image, compression should not be used. Rather, you'd like to store it in as is, as much as possible. If you're using something like PySpark, should you use things like Mongo? I wouldn't say that you need something like MongoDB for something like this. But just using cloud storage is typically a good solution that I've seen overall. How to check bias in data, not a selection bias. How to check bias in data that is not a selection bias? Because of course, yeah, the data set that you have at hand, again, this has been handpicked, right? So let's say that I gave you the example, right, of autonomous drive, when you had a stream of data that was coming in, and now you have to pick, what are the images that are of interest. Manually, of course, you have selection bias will automatically trickle in. But if this quality, or if you can come up with metrics that tell you about the image not before, prior to selection. So you have to come up with a smart metrics that go before, selection in order to come up with that. So that's why SSIM is definitely a good metric to tell you how dissimilar they are. Automated systems like a deep learning, algorithm that's going to tell you what the metadata or the tags are, they are also useful. Anything that is going to give you more information about the image, so that you pick the images and they are not selected dissimilarly, is useful. So that's a great question, and that needs to be a huge amount of thought that goes into it. All right. I apologize again, guys, for that the fact that you were not able to see the code book. I'm going to make that available, and again, I'm going to edit the stream so that you can see it in most of the image. I'm again going to see you next week, and next week we get into model pipelines. If you have any other questions, please leave it in the chat below. Otherwise, thank you so much, and I'll see you next week. Same time, same place.